Okay, let's get started. Good afternoon, everyone. Thanks for attending today's webinar on blower door testing. This training is provided by the Colorado Energy Office with training materials created by Tank Inc. Robbie and I have been working with the Energy Office for the last 5-6 years now, Robbie, right? Plus, to provide trainings just like this one. We offer a wide variety of trainings. This is one within a series, so if you are interested in attending any of the others, feel free to register for those, and I'll send those links so that you can share that registration link with other folks that you know as well. We do also offer tailored group trainings, and so if you have a specific topic, basically we can train on anything that's related to the energy code. And then we also offer role-based trainings, which is like a deeper dive through the perspective of you as the market actor that's applying the code. So if you're a contractor, a building official, permit or plan reviewer, permit counter technician, inspector, you name it, we have a training that's tailored to your role and how it relates to energy code compliance. So if you're interested in any of those, feel free to reach out to me and we can get you set up. We have a bunch of resources available, including a code adoption toolkit that's got significant changes, cost estimates, different guides, checklists that can be tailored to your jurisdiction. But my favorite resource is the Colorado Codes Helpline. And you can submit a question on any of the I codes, and a subject matter expert will get back to you in just a couple of days' time. So whether you have a question, whether you're a plan reviewer looking for assistance with reviewing a permit application, we're here to help. Or if you're a homeowner and you have a question about code applicability, we can also answer those questions. So with that, I'm going to go ahead and stop sharing my screen. I am going to launch a poll. If you all could take a minute to fill that out, that would be very helpful for us to continue to improve on these webinars. And with that, I will pass it over to Robbie Schwartz from Tank, who will be presenting today's sessions on blower door testing.
Great. Thank you so much, Erica. You'll see that the title has been broadened just slightly to include duct leakage testing and ventilation testing, basically the three main tests that are required by the IECC. And I just wanted to make a quick note that next week's presentation on radon testing has also been broadened to talk a little bit more about the radon issue and also mitigation things because testing is a pretty small part of the radon puzzle. So join us next week as well. Today we're going to talk about these tests. We'll talk about why we care about diagnostics. We'll talk about blower door, duct leakage, and ventilation testing. So the first thing in the 2024 IECC, the intent statement's been broadened quite significantly to talk about these minimum efficiency requirements that result in maximum levels of energy efficiency that are safe, technologically feasible, life cycle cost effective, and considered economically feasible. These things that are addressing air and air movement in our house is really the most cost effective way to get an efficient house. And we see that really come to fruition when you look at the 2012 IECC and the determination that the Department of Energy made during that cycle that demonstrated that about almost 20% efficiency gains were gained in that cycle, really on the back of the requirement for blower door testing in all the houses that we build. When we do blower door testing, we have to go back to the code and understand how the code is looking at the building thermal envelope, because we have to have that clear boundary condition between conditioned space and exempt unconditioned space in order to do a blower door test. In essence, we need that boundary condition for duct leakage testing and for ventilation testing. But the boundaries change when we talk about ducts and ventilation. We're talking about the boundary between inside the duct and outside the duct. So the boundary of the duct itself versus the blower door test, we're talking about inside the house versus outside the house, conditioned space versus exempt unconditioned space. And we have to be able to clearly define what that conditioned space is, because this is currently primarily a volumetric measurement, and we need to understand what the volume of air is inside that house. So when we get that sound building thermal envelope, ultimately we are being able to gain better control and predictability of airflow, thermal flow, and moisture flow inside those houses, and gets us to this question of why do we ultimately care about diagnostics? Because they ultimately help us achieve the requirements. One of my mentors used to always say, you get what you inspect, not what you expect. And if we're counting on air tightness in our building thermal envelope and our duct systems and our ventilation systems to provide the right flow of air, then we have to be able to test to ensure that that's happening, because you can't just look at the building thermal envelope and know that it's airtight. So there are these mandatory requirements in the IECC that helps us achieve that air tightness requirements there. And then ultimately we're required to test not only the air leakage of the house, but the duct leakage as well. The other thing that this does is that in these performance paths through the code, we gain additional trade-off flexibility so that we can potentially trade off house tightness for R value, or duct leakage and duct location for R value, or other things, so that we have more flexibility in how we ultimately design and construct our building assemblies there. Now, to be clear, what we often call the res check, or the area weighted U value compliance approach, that uses a software in the prescriptive compliance approach for code compliance, that only gives you the ability to trade off U values and R values. So you do have to go to the simulated building performance approach or the ERI approach, the R405 and R406 pathways, in order to get this additional flexibility. But it is there, and you can take advantage of that. So jumping into blower door testing itself, obviously we can test a variety of different building types out there, but we have to have an understanding of how air moves, and air moves in our homes in particular. So the first thing that we need to think about is what has to happen for air to move. We have to have a hole, or this boundary condition that we talked about, but you have to have a hole in that boundary condition, and you have to have some pressure across the boundary condition in order for air to move across that boundary there. So when we talk about pressures across the building thermal envelope, it's always important to know where you're standing and what you're referencing to the outside. So in most cases, with regards to blower door testing, we're standing inside the house and we're referencing outside the house. So I have a tube that's measuring the pressure inside the house with regards to outside the house. So I'm always understanding the boundary condition that I'm measuring across there. We have certain ways that pressure is created across that boundary condition of the building thermal envelope, and we call those things the stack pressure, the wind pressure, and mechanical pressures that are created there. And these are basically forces against the surface of that boundary that either create a positive pressure or a negative pressure in specific zones there. So that's what we're trying to determine there. And then ultimately, we're measuring that pressure difference across the boundary. And when we do these diagnostic tests, there are a variety of ways you can measure it. HVAC contractors often use inches of water column, but we use a metric unit called pascals, or newtons per square meter there, in order to do that there. So we have this sound building thermal envelope that's defined by the code, and we are determining what the pressure difference is across that hole, or across that boundary is there. So you can think of this balloon, for example, the rubber membrane of the balloon, as the boundary, or the building thermal envelope there. And if I have equal pressure and no hole across that balloon, then the balloon is going to remain inflated there. But as soon as I put a hole in the building thermal envelope or in the balloon, some rubber membrane, then the dynamic changes quite a bit. So if I untie this balloon, then the balloon's going to shoot across the room because I have greater pressure outside than I have inside the balloon. So again, I need the pressure difference across the building envelope or the rubber membrane in this case, and I need a hole in order for air to move across that hole there. And so it's much easier for us to control the holes in the building envelope rather than the pressures there. So the code is all about trying to figure out ways to ensure that we have a tight building envelope, that we sealed up all the holes, and therefore we have the air barrier, air sealing, and insulation installation table here, which is basically, you could think of it as a checklist for how to create an airtight house that's going to meet the requirements of the IECC here and seal up all those holes, because I can't really control the air leakage that happens across that holes that are driven by these different pressures, the stack pressure, the mechanical pressures, and the other pressures that we might see in that house. So this table details out these different components, and you can use them as examples of what you're going to see in the house and how to address them from an air barrier and air sealing perspective and from an insulation perspective. But what that table is ultimately getting at is how air moves through our houses. So we measure airflow in cubic feet per minute of air moving through the building envelope. So again, we have to have that sound building envelope that we're measuring across. And the notion is that that envelope traps a specific volume of air inside of that house. And that volume of air doesn't change once you've been able to define and clearly define that building thermal envelope air barrier system there. Because remember, the building thermal envelope is the alignment of our thermal layer and our air control layer all the way around the house, and including that portion that's going across the dirt at the bottom of the foundation. There's our slab, for example, in a basement, or the dirt floor in a crawl space that we need to contain the air movement through. So whenever we have a cubic foot of air going through the house, and we can think about a cubic foot of air as a number of basketballs that are going into the house, then the cubic feet of air has to leave the house. So if a basketball enters the house through wind pressure, then it has to leave the house as well. So air in equals air out, and that's kind of the fundamental building science there. So air is a fluid, and it's a fluid just like water's a fluid. We need a hole, and we need some type of driving force or pressure difference across the hole in order to get air to move in and out of our houses. And we measure it in cubic feet per minute there, or about the size of a basketball going in and out of our houses here. So diagnostics, again, you get what you inspect, not what you expect. It gives us a way to measure or quantify and do quality assurance on the building thermal envelope. We use blower doors. We can do pressure diagnostics with those blower doors. We can measure duct leakage and ventilation flow. We can do levels of HVAC commissioning to understand how much airflow a system is actually achieving there. So there are a variety of different things we can do with diagnostics, but the code is asking us to build our houses tight and ventilate them right, and we're trying to understand, has that actually happened in that particular house in relationship to what the code is requiring there. So when we do the blower door test, we have to measure the air leakage of that house using a blower door that's depicted here. And now we have to actually follow a standard for how to do that. And primarily we're using the ANSI ResNet ICC 380 standard, which incorporates the ASTM E779 standards and these other standards. So now that the ANSI ICC standard has been created, that's the primary standard that we're following, and that makes a lot of sense because the majority of the people that are doing these tests are energy raters, and they're already following these standards. So it makes a lot of sense that we've kind of defaulted to the ANSI 380 standard there. Now, where tested, the maximum air leakage rate has changed a little bit in the 2024 IECC when you're using the prescriptive compliance option. They've made kind of different air leakage rates depending on your climate zone. So in our climate zone here in climate zone 5, that hasn't changed. But as you start moving up into the mountains, into climate zone 6 and 7, you now required to have a slightly more airtight house to 2.5 air changes from 3 air changes. And you can see that in climate zones 0 through 1, that the tightness has gotten a little tighter as well from 5 air changes to 4 air changes there. Now, because air leakage can be used as a method to trade off for less R value potentially in a building component when you use sections R405 and R406. They had to put in a maximum air leakage rate of 4 air changes there, but you see that they've also introduced a secondary method of measuring air leakage, which is a CFM per square foot of building thermal envelope area there as an alternative means of measuring it, because it turns out that the volumetric measurement in air changes per hour isn't the most effective way to measure air leakage there. So we'll talk about that in a little bit here, but this section has been made significantly more clear than in the 2021 IECC, where this first came into account, where they have a different air leakage rate for the performance compliance approaches versus the prescriptive compliance approaches. So when you read it in the 2021, you might think that they were lessening the air leakage base requirement from 3 air changes to 5 air changes. But that's only in relationship to the performance compliance approaches R405 and R406, because you potentially can do this trade-off that doesn't happen very often, where you might put more insulation in the house in order to have a leakier house. In most cases, the trade-off works where you're tightening up the house in order to reduce the R value in certain locations around the building, not the other way around, but they wanted to put in a backstop to guard against that. And this is how it's expressed in the 2024 IECC, which again is much better than the way it's expressed in the 2021 IECC. So the basics of a blower door test is putting a device, a blower door, into the building thermal envelope. It's an airtight assembly with a blower, fan blower, inserted into this nylon fabric here. And ultimately, we are depressurizing the house. So we're sucking air out of the house and forcing air to come back into the house. Remember, air in equals air out, or air out equals air in, the basketball analogy that we used before. So if we have a really tight house here, we're going to, I'm sorry, if we have a really leaky house here, we're going to suck air out of the house. We're going to throw basketballs out through the fan, and basketballs are going to come back in through holes in the building envelope. And the lower picture here shows that if we have a really tight house, less air is going out, and therefore less air is going back in through the holes in the building envelope. This is a scientific test that's a repeatable test because of the standards that we're using. So that if I do the test in Colorado and somebody else does it in Massachusetts, we're doing the test in the same way, and we're going to get repeatable results in that way there. But it is measuring a moment in time. And so we need to understand that, because at different times of the day, the wind might be blowing, or the stack effect might be higher when the temperatures are different inside and outside the house. So the leakage, we're basically getting an understanding of how leaky the house is, but it's not representative of how the house is going to leak every minute of the year, every day of the week, for example, throughout. Ultimately, how we're measuring that is we're using the pascals of pressure across the building thermal envelope, and then measuring the cubic feet of air that's moving through the fan. And so we need to talk a little bit about pascals, because they are a very powerful unit of measurement in the metric system that gives us the ability to measure positive and negative pressures across the building envelope. It's similar to measuring using water columns. So I'm going to give us an analogy of water columns. 1 inch of water columns is equal to 250 pascals of pressure there. One post-it note pushing on down on your hand is equivalent to roughly 1 Pascal. And another way of thinking about it is the pressure that you might see in your tires is equivalent to about 250,000 pascals roughly there. So again, it's a small unit of measurement, but it's a really powerful unit of measurement because it only takes a very small negative pressure to backdraft an atmospherically vented water heater, for example, and get the byproducts, that carbon monoxide flowing inside the house rather than outside the house. So we always want to understand the units that we're measuring it in and why we're using those powerful units of measurement in pascals is because they get us down to the details that we need when we start doing combustion safety testing with a blower door or other things, other types of pressure measurements that we might do with a blower door beyond just the blower door test itself here. So the blower door test, again, helps us understand how airtight the house is, how much leakage is happening under relatively natural conditions, because when I depressurize the house to 50 pascals, it's roughly equivalent to a 20 mile an hour wind on all surfaces of the house kind of simultaneously in these test conditions here. We can see how successful we've been at actually air sealing that house, how much control and predictability we're gaining over the airflow, moisture flow, and thermal flow that's happening throughout that house. So we want to close up those holes and limit the infiltration and exfiltration that's happening in that house. And then we'll see as we talk about duct leakage that we need the blower door in order to be able to measure duct leakage to outdoors, which gives us an additional trade-off credit in our houses. I wanted to talk a little bit about the difference between infiltration or just random air leakage in our house and ventilation, because that's confusing to some people. We need to understand that infiltration is basically this uncontrolled air movement from inside to outside the house or from outside to inside the house if we change the word to exfiltration instead of infiltration, whereas ventilation is this controlled process where we bring mechanical ventilation systems into the house in order to bring air in and air out in a controlled and a predictable fashion. Now, we might be using holes in the building envelope to ventilate the house as well if we're using an exhaust ventilation strategy or a supply ventilation strategy, but we're putting that that fan in so we know exactly how much air is moving through the holes in the building envelope, and we're putting it on a timed system there so we have that better control and predictability there. And the building science is basically saying that we need that control and predictability of ventilation air, and we need the tightness of the house in order to gain better control and predictability again of airflow, thermal flow, and moisture flow inside of those houses there. So a portion of the supply air may come from the outside through holes, but again, we're recirculating that air into the house to be able to help the occupants of that house be more healthy and to get background moisture control inside of our homes there. So one of the last things I wanted to talk about here is new to the 2021 IECC is that if you're dealing with attached housing that's 3 stories or less, so basically multifamily housing there, you are now allowed in the 2024 IECC to do a sampling of testing in those units instead of having to test every single unit in a 3-story multifamily building there. So you want to, if you're in charge of a jurisdiction, you want to take that into account because you'll definitely be asked about that. And that brings up this notion that there are some different types of blower door tests that you're also going to be asked about. So if we have a detached single family home, it's different testing that enclosure versus testing an enclosure that's inside a multifamily building that's 3 stories or less here. So when we're talking about attached housing, we're often talking about, is there leakage that's happening across the wall system or the floor system that is adjacent to additional attached units that are in that building there. And I can tell you in townhouses and duplexes that there's very little leakage that's happening from unit to unit. Most of the leakage is associated with these shaft liner area separation walls and the 3/4 inch gaps that are required by the assembly, but are attached to the outside or attached to ventilated attic spaces there. But when we get into multifamily buildings, that dynamic might change because we have a greater, bigger thermal envelope that is the boundary of there. So you might be asked, can I do compartmentalization testing? Can I do whole building testing? Or can I do guarded testing when we're doing these types of blower door testing on multifamily buildings that are governed by the residential energy code there? My favorite is the single unit compartmentalization test, because what that does is it ensures that not only from an energy perspective are we creating an airtight house to stop the leakage from inside the unit to directly outdoors through maybe the front wall of this building here, but I'm also dealing with health and nuisance odors that might be coming from adjacent dwelling units, from units that are adjacent here that might be leaking across this assembly here. So if this is tight, then the unit's front wall that's adjacent to the outside is going to be tight as well. And we're going to have less energy issues, but I'm also maybe not going to be able to smell the guy next door that's smoking pot or whatever they're doing next door there. So I like the compartmentalization test. It's the most economical testing to do, but you might be asked about the other types of tests. Now, this is the test where that other metric has come in, where we're getting the CFM per square foot of unit enclosure or envelope area there. And we're trying to figure out how much leakage is happening through the actual building envelope rather than just this volumetric measurement. Now, the other thing that this all brings up is what we call guarded testing here. So if I do only want to know the efficiency determination of this unit here, then I only care about the leakage at the front of the building and at the back of the building here. So those two walls of this center unit are what I care about from truly the energy perspective there. And in order to get just that leakage there, I have to put in blower doors in the surrounding units in order to take out the leakage that is happening across the common wall or common floor between these units here. So if I depressurize all of these units simultaneously to 50 pascals inside the unit in relationship to outdoors, then I've taken away the leakage that's happening across the wall, and I can measure just the leakage that's happening to the outdoor unit. Now, that is definitely possible to do, and you might be asked if I can do that in your specific jurisdiction. But what I would say is that it's costly because I have to have a number of blower doors set up simultaneously to be able to do that, and a number of technicians out on site. So again, I think the compartmentalization testing is the most cost-effective testing that's out there. Now, the other thing that you can do in these buildings, although this is a 4-story building rather than a 3-story building that would be governed by the residential code, is test the greater building thermal envelope. So if I can connect all of the dwelling units and the common areas to the blower door, then I can do a greater building thermal envelope test on that building just in itself. I might need 6 blower doors in order to do that, to depressurize it to 50 pascals, or potentially you might have to change your metric to 75 pascals of pressure there inside the building in relationship to outside the building. But you can do that and you can get the results there. So again, there are a variety of different ways to do the blower door testing, and you might be asked about that in your particular jurisdiction. I think the last thing I wanted to talk about with regards to blower doors is that you can utilize the blower door to measure other things, like is the garage actually separated from the house as is required by the code. Now, only one jurisdiction that I'm aware of in Colorado requires this particular test, and that's the city of Fort Collins, that requires that the garage be measured and proven to be separate from the house because of the health and safety issues that are associated with that garage connection. But it's a very simple test to do. If you have a blower door already set up, it takes an additional maybe 5 minutes, 10 minutes to get that number and ensure that the garage is separated. So you can do these, what we call zonal pressure testing, to ensure that a specific zone or building cavity, or in this case, garage, is actually separated from the house there. I guess while I'm talking about garages, I should also make it clear that the garage is always outside the building thermal envelope. Even if that garage is heated and conditioned and insulated, you never include the garage space in the volume of the space that you're trying to test for air leakage when you're doing blower door tests, because of all the incidental stuff that we store in our garages that are health and safety issues, let alone our car that we start up and put all that carbon monoxide in there, but we store paints and gas and insecticides and all that other stuff in the garage, and we want to make sure that that air is always outside the habitable space of the house there. Okay, so let's move on to duct leakage testing here. From a duct leakage testing perspective, we have to clearly define the duct system, and the 2024 IECC has taken another stab at defining the duct system so that we're crystal clear that we're including the entirety of the duct system, including things like filter boxes and air handler cabinets and other transition pieces in that duct system. And it's all the way out to the duct boot and the surface of that duct boot, not inside the duct boot. So we want to tape off these systems appropriately to ensure that we are getting all the duct system incorporated when we're measuring the duct leakage that's happening there. And we have to take into account and remember that building cavities are excluded. We are not allowed to use building cavities as pressurized duct systems in the International Energy Conservation Code. That happens in R 403.3.2, where it specifically says that we can't do that. And this is an example of a building cavity that's being used in a ranch-style house on a summer day. You can see how the duct system is, in this return, is pulling air back to the furnace cabinet to recool, in this case, because it's a cooling season that's being represented here. And you can see how hot air that's in our ventilated attic is being pulled in to the house through this ducted return. This return that is utilizing this building cavity there. So you might be asked about this because there is a little bit of discontinuity in the codes. In the IRC mechanical section, it does say that you can use plenums and building cavities in certain ways, but you have to remember the idea of applicability. This is a section that's in every code that basically says the most restrictive requirements shall govern, and it's really important that we don't use building cavities here. It also is important because of how our duct systems are designed. Our duct systems are designed specifically, we see more building cavities on the return side than on the supply side. So on this return side, this opening here that is defined by this grill opening here is defining how much air has to go back to the furnace cabinet to properly heat and cool that house there. When in reality, this hole in the bottom plate is actually governing the amount of air that can get back to the furnace cabinet to cool or heat that air in that house. So notoriously, our houses are under-returned when they're using building cavities because of this type of scenario here. But we see that it's also very difficult to air seal a building cavity. And, sometimes you get these other things that are inside building cavities that you are prohibited to have inside of a ducted cavity that's trying to return air or supply air to that house there. So we want to make sure those things are not incorporated into those systems when we're measuring them. So how do we actually measure air leakage through a duct system? This kind of protocol takes us through the steps. So we start by blocking off all the known openings, all the supplies and returns in that furnace system there, that HVAC system there. We install our duct leakage testing device, sometimes called a duct blaster. There, when we install a pressure probe inside the duct so that we can measure the pressure inside the duct in reference to outside the duct, because we're going to use that duct testing fan to introduce a common pressure of 25 pascals inside the duct in relationship to outside the duct. So I'm pushing that fan pressure in, and it's going to leak out of random holes in the building envelope if I have blocked off properly the known supply registers and return registers in that house there. So I'm pressurizing the fan. In this case, I'm pressurizing the ducts, and I'm getting 25 pascals inside the ducts in relationship to outside the ducts. And basically doing the same thing that I did with the blower door test. And in order to achieve that 25 pascals in the ducts, I want to measure how many CFM of air is going through the fan to achieve that pressure. And that is equal to the amount of air that's leaving through holes in the building, through holes in the ductwork system there. So I can measure, in this case, I've got a smart gauge here, a smart manometer or pressure gauge here. And you can see that here I'm measuring pressure on this channel here, and I'm measuring that pressure as if it were at 25 pascals. And so if I were able to, this smart gauge is basically able to tell me if I were at 25 pascals of pressure, I would get 32 CFM of duct leakage out of that system in this particular case here. Now, I don't know if that is a good number or a bad number until I take it to the requirements of the IECC. So we'll see if that was a good number or a bad number here in a second, but it is telling me I am leaking 32 cubic feet of air per minute through the holes in that duct system. Now, the code tells us that we have to make these systems airtight, and as we require the system to get tighter and tighter, these manufactured joints start leaking more and more. So these manufactured joints need to be air sealed. Basically, every seam, every joint, every connection point needs to be air sealed. And we always recommend that you do that with a mastic product rather than a tape product, because the mastic will last over time there. And our houses, we hope will last, be those 100-year-old houses. In the 2024 IECC, the duct leakage requirement has changed a bit, or at least how they are talking about it are reflected in a table now rather than in just language in the code. So if I have space conditioning equipment isn't installed, or if all the components of the duct system are installed, depending on the number of returns in that house, I can either leak 4 CFM per 100 square feet of conditioned floor area that the system serves, or 6 CFM, depending on the number of returns up here. As I get smaller and smaller square footage, this leakage rate, dependent on the CFM per 100 square feet, gets smaller and smaller. And so they put in a fixed rate of leakage if you're under 1,000 square feet. So for example, if that house that we just were looking at back here was 1,000 square feet, and the system, all the components of the system were installed, I couldn't leak more than 40 CFM of air. And in that case, I leaked 32 CFM of air. And therefore, I've been able to determine that that house passed its air leakage test for the duct system that was installed in that house. And then you can see that if all the components are installed inside the conditioned space of the house, you're given even more leeway in the amount of duct leakage that you have. But now in the 2021 and the 2024 IECC, regardless of where the ducts are located, they have to be tested there. So that's the big thing. So you want to take a look at this table and understand this table and kind of the requirements. And I would say that now in our duct leakage reporting, we're going to have to include the number of returns that are in that house so that the code official actually understands where you got your duct leakage target for that particular house. Just like with the blower door testing, you're allowed now to do sampling in multifamily buildings, but those duct systems now have to be tested regardless of if they're in the inside the building or outside the building. Whereas in codes up until the 28, up until I guess the 2021 IECC, if ducts were inside the conditioned space, you actually didn't have to test the ducts at all there. Now, what's been made even more clear in the 2024 IECC is that if you're using the R405 or R406 compliance options there, you have to do an additional duct leakage test, and this is called duct leakage to outside, so that you can get the benefit of additional trade-offs. If that duct is leaking nothing to the outside, then you're going to build your trade-off budget so you can maybe trade off that slab edge insulation or that continuous insulation on the outside there. So this is a test that needs to be done, and in order to do this test, you need to remember the way that air moves. We need a hole and we need a pressure across that hole. And you also need a blower door and a duct tester running simultaneously during this test in order to do that. So we set up the test in the same way that we do for total leakage, where we block off all the supplies and returns in that house. But we also set up a blower door here and a duct blasting fan or a duct testing fan there. So we use the blower door to pressurize the house and the duct system here. So the blower air is going into the house to pressurize to 25 pascals and also going into the opening of our duct testing device here and into the duct to get to 25 pascals of pressure inside the duct. So if I have 25 pascals of pressure inside the duct and outside the duct, then this hole, for example, we're not going to have air leaking across that hole because I need those two things. I need the hole, but I also need the pressure across the hole in order for air to move through the fan. I mean, through the hole. So air isn't going to be leaking out through this hole, but this hole in the attic, air is going to be leaking out that hole because this attic pressure is not at 25 pascals of pressure, while the duct is at 25 pascals of pressure. So hopefully that makes sense. Ultimately, what we're doing is then once we have the pressure inside the duct and inside the house, both at 25 pascals of pressure, I'm going to measure the pressure inside the duct, and I'm going to pressurize, or I'm going to use my duct blaster to zero out that pressure and measure how much air it takes to, in essence, close off this hole there. And after I've done that, it gives me a number that is giving me the leakage of air outside the building envelope, which is the true energy penalty. So if I have less duct leakage outside, I have more trade-off credit that can be used there. So it's a little bit complicated to understand, but ultimately that's what the test is getting us to do here. So we use these testing devices to be able to tell us about the flow of air through the duct systems, how much is leaking out, but we can also do some additional commissioning diagnostics as well through pressure diagnostics, through measuring the flow through the duct system with these two methodologies here, and or a new standard 310 that's been developed that can potentially give you more HERS points the better your system has been installed and developed. And the hope is that possibly in the 2027 IECC, that standard 310 will be adopted into the code so that you can get better assurance that the system that's been installed in the house is actually going to perform. That goes beyond just doing duct leakage testing there. Now, there are some other trade-offs that are given for the R405 and R406 pathways if dependent on where those ducts are located. That goes beyond just duct leakage. So you want to look at those requirements in the code as well. If a builder is using the R405 or R406 compliance options in the code. Okay, so the last 15 minutes we have here, we're going to talk about ventilation, the V and HVAC there. So that begins with this kind of question of, can our houses be too tight? And since we don't have time to put out a poll there, I'm going to give you the answer. The answer is no. Houses can't be built too tight. Ultimately, we want to build them as tight as we possibly can because it goes back to that notion of gaining control and predictability of airflow. And air is basically a transport mechanism. It transports heat and pollutants and moisture in that airstream. So if I can gain control and predictability of the airflow through the house, I gain not only efficiency control, more efficient house, but I get a building durability control and predictability. But as we build our houses tight, we also can never remember or never forget that we are asking a different question. So the question we should be asking is our house underventilated? And still, although this has been a requirement in the code since really the 2009 IECC or possibly even before that, we are getting houses that don't have clear ventilation systems that have been installed in the code here. Ultimately, why I'm talking about this in this session is because we now have a requirement not only to have the ventilation system, but we also are required to measure the flow of air so that we know that it's meeting the requirements of the code here. So the code has adopted the sound building science that we want to build our houses tight and we want to ventilate them properly there. So we want to understand the difference between air leakage and mechanical ventilation. We talked about this briefly before, but air leakage is that random and uncontrolled movement of air in and out of our houses, while mechanical ventilation has control and predictability. We have a specific rate of air that's moving through a fan, and we're setting that fan at a specific schedule. Now, the schedule might be running 24/7, but we know that, and therefore, since we can measure the flow rate, we know how much air is coming in and how much air is going out of that house. There. Now, some of these ventilation systems can provide additional features like knowing exactly where the air is coming in and going out, or being able to add filtration and distribution to the notion of ventilation. So when we start talking about them, we start talking about more balanced ventilation strategies, and balanced ventilation strategies are starting to be required in specific climate zones, and that climate zones is going to ultimately keep moving down in the different code cycles. And it won't surprise me at all if in the 2027 IECC, the ventilation cycle moves down to climate zone 7, which I'll show you here in just a second. But before we get there, I just wanted to show you that ventilation is a quote unquote mandatory requirement of the code, regardless of how airtight the house is now there. So we have to understand ventilation and how to measure if the ventilation is meeting the requirements of the code. This is where we get the idea that balanced ventilation is now required in climate zone 6, 7, and 8. And in the 2027 IECC, it won't surprise me at all if it moves down to climate zone 5. But I also know that there are some requirements to make balanced ventilation required everywhere, regardless of your climate zone, because it's simply the best ventilation strategy that's out there. With the least complications, I guess I should say. Now, these ventilation systems also have to be efficient. because you are using an electric fan to ventilate the house properly. So they have to have at least 65% recovery efficiency at 32 degrees, which means that the fan needs to be efficient, but also its ability to recoup heat that might be leaving the house, or moisture that might be entering the house, that has to be efficient at doing that as well there. So you're really talking about ERVs or HRVs, heat recovery ventilators or energy recovery ventilators, versus kind of random components that you can create balanced ventilation strategies with here. This is where the code requires us to measure ventilation, and it's not just limited to whole house controlled mechanical ventilation. We're also measuring bath fans, or what we call spot ventilation, in our bath and laundries, but also kitchen hood ventilation systems also need to be. So any ventilation that is governed by, I think it's the mechanical section in the IRC. It's 1105, I believe, in the IRC that talks about the actual flow rates through these fans. That needs to be measured now. Now, in multifamily buildings, just like for blower door testing and duct leakage testing, you can use a sampling protocol if the jurisdiction will allow you to do that. Now, for measuring ventilation, for whole house control mechanical ventilation, we're relying on the ASHRAE 62.2 standard to be able to tell us what the flow rate for that specific house must be. And now we have to actually measure that flow rate. So there's a variety of different devices that you can use to measure flow rate. We'll talk about some of those here. For exhaust ventilation, some of these fans, you can fix the flow rate, and they use a variable speed fan here. So you can set the flow rate here, and this fan will compensate for the static pressure. The static pressure is the measurement of the resistance of flow through the fan, and it will compensate and give you that flow. You still should measure it to ensure that it's getting there, and you would use a flow hood to measure, or a flow box to measure the flow of air through a bath fan that's exhausting air from inside the house. Now, these bath fans are required to be able to push at least 50 CFM of air, because they're only operating intermittently, not continuously here. And you can see this particular fan was only measuring 25 CFM of air here. So you should be talking about this with your builders now, because if they aren't consciously thinking about the fan that they're installing and also how they're installing that fan, you're not going to be able to meet these requirements. And the Energy Star program that's been requiring this flow measurement for years has definitely shown us that a typical builder grade fan that's rated to push 50 CFM of air does not push 50 CFM of air when you put ductwork on it there. So this flow box basically gives us the ability to measure the pressure inside the box in relationship to outside the box, and then go to this chart here and says, if I'm measuring 3.7 to 3.8 of air and my opening is of this E1 size, that it's pushing 85 CFM of air. And again, it's very precise. It works very well, but we should give some opportunity for the builders and HVAC contractors to know that this test is coming, and that they need to up their game there a bit with regards to how they're installing the fans in these systems here. Now, balanced ventilation systems are a little bit more difficult to test if they haven't provided you with these pressure ports. We have to measure the pressure on the incoming air, the outgoing air, and the air that's coming from the house and then going to the outside, if it is 4 sides here. And it has to be balanced in order to do that. So these pressure ports make it easy to test. If these pressure ports aren't available, then you're using a device like this to get up into the duct to measure the pressure inside the duct and equate that pressure into a flow number there. So it's a little bit more difficult, and we need to help the HVAC community understand that we are now required to testing these systems. So they need to provide means for us to test it without damaging their systems. Supplied ventilation systems are notoriously difficult to measure. And if you're going to use a supply ventilation system, I always recommend that you put an iris damper in it, because I can not only measure the flow and the CFM through this iris damper, but I can then also I can control the opening and set it so that it's pushing the correct volume of air through the system that's required by the IECC. Otherwise, you're going to be poking holes in the duct and putting these types of devices in to try to understand how much air is flowing through that ventilation system. The last one that we are going to be measuring is kitchen hood measurements. Kitchen hoods, there are some exceptions. If you have less than 2 bends and you have a 6-inch duct attached to that fan, then there is an assumption that the system is able to push the minimum 100 CFM of air that's required to flow through that kitchen hood. Otherwise, you're going to be using flow boxes or flow hoods to try to measure the flow of air that's moving through that kitchen hood there. Okay, so this is just an example of why, once you put duct onto a fan housing, that you might not be getting the flow that you are required to have there, because any elbow in the duct, any elbow right out of the fan housing here is going to create additional fan static pressure that the fan is not going to be able to overcome here. So we don't want to tie our ducts in a knot there. We want that smooth duct here. So ultimately, you get what you inspect, and that's why these requirements are in the code. The code gives us specific flow rates that we need to meet, and we don't know if we've met them unless we test it. Testing isn't difficult to do. It's just making sure you have that time and that you're seeing the house at the right time frame in order to make a difference. And that's particularly important with regards to ducts. It's much more beneficial to test that duct at a rough stage of construction so that you could fix the duct leakage if there is an issue there. You want to look for certified technicians that are doing this duct testing. We are doing some training in rural parts of the state to try to build the infrastructure of technicians that can do these tests, so that the state code that's coming out can actually be enforced and utilized out there. And you also want to use the new standards that are out there for duct testing and for ventilation and whole building blower door testing as well. The code does provide a lot of flexibility, and that's a big reason why these tests are being done, so that we can quantify the leakage, so that we can say, our house is substantially airtight. They're going to leak less air out. Therefore, I might need less insulation to control the conductive losses if I've got better control of the convective losses inside that house. So I'm happy to stick around and have any comments or questions, but if you want to reach out to me as well, you're more than happy to get an email or a phone call. So take down that information as well.
Thanks so much, Robbie. We do have quite a few questions for you, so we
Great.
will get through as many as we can.
Yeah.
First one, can the duct fan be connected to a return or supply duct? If no, why?
Okay. When you're doing duct leakage testing, you always put the duct fan on the return side of the system, because you're putting your pressure probe to measure the pressure, the constant pressure that you're introducing inside the duct in relationship to outside the duct on the supply side of the system. So it gives you a better indication that you've uniformly pressurize the duct system in order to figure out how leaky it is.
Perfect. Thank you. Okay, why does the number of returns dictate the duct leakage amount?
Uh, it's a pet peeve of mine, but the Energy Star program utilizes that number of returns requirement. Ultimately, Energy Star's goal is different than our goal. We have a common goal of creating a more efficient house, but Energy Star has an additional goal of participation in their program. And because um, certain states basically don't enforce the building cavity requirement. You have systems that are leakier with more returns when they're using building cavities. And they want to keep their numbers up while promoting tighter duct systems uh, in jurisdictions that aren't promoting not using building cavities. So they move to this allowance for more leakage with more returns. It is true that you have more ducts with more returns, but you can make hard ducted systems airtight. And so anyway, this allowance that was given in the Energy Star program, somebody made a proposal to make that allowance allowable in the IECC, and that proposal was accepted. And I'm going to try and get it out in the 2027, but right now it's accepted there, so you can utilize it.
Gotcha.
I guess
Thanks,
I'm
Ron.
sorry. I'm going to say one more thing here, but
Yeah,
also because we now have the requirement to test for duct leakage, regardless of where the ducts are. There is a little bit of um, less impact of of the number of returns because the ducts that are inside the building envelope are leaking air inside the building envelope. It's not as efficient as if they weren't, but it's less of a penalty ultimately there.
gotcha. Okay. All right. Next one is the duct leakage to outside test requirement for the 2024 IECC? How could you know if there is no duct leakage to the outside before the home is built and trade off slab insulation per your example?
Um, you can't know specifically unless you're proposing to install all your ducts inside the uh, building thermal envelope that's defined on your plan set. If you're doing that, you can be pretty assured that you're going to have very little duct leakage to the outside there. But if you are proposing at the time of permitting that you're going to have no duct leakage to the outside, you have to prove that at the end of the process when you are utilizing the R405 or R406 process there. So it does kind of raise that question, I guess. If you didn't achieve that, if you didn't achieve what you proposed to do, what do you do now? And the reality is what a jurisdiction probably should make you do is to air seal your ducts at a final stage of construction, which is um, utilizing AeroSeal, which is a propellant that you blow through the ducts, is really the only way to do it there. So if you're proposing that, you're most likely you're working with a builder that is going to try to ensure that they're going to meet their requirement because they don't want to take on that additional expense of AeroSeal or some other way of sealing the ducts at a final stage there.
Gotcha.
I guess I'm sorry. One more thing.
No, you're fine.
This is another reason why you want to test the ducts at a rough stage of construction, because if the ducts are tight at a rough stage of construction, it's very unlikely that they're going to leak to the outdoors as well, even if they're located outside the building envelope.
For sure. Okay. So this next question is a bit of a math problem.
Okay.
Using the 0.22 CFM per square foot, as I was doing the math, I have a home that is 940 square feet. That would mean I should see a blower door reading of approximately 206.8, which is about 0.6 air changes per hour. That's extremely tight. We just weatherized a home that was 1.9 and installed an HRV because of the condensation building up on the walls. Am I doing my math right with that calculation? As that doesn't seem right.
You might be doing your math right. I'm not gonna check your math here. What you're pointing out is a reality that the two metrics are not equivalent directly together, and they can't be equivalent. So the code is choosing something that is as close as possible to the air change per hour metric. What we're ultimately trying to do is to move away from the volumetric air change per hour metric over time in the codes there. So as we introduce it, it's 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 going to benefit houses that are smaller and houses that are attached, because often the metric is greater, is allowing more leakage than 3 air changes per hour in our climate zone there. In your specific instant, it wasn't, but that's generally not the case there. Um, the other thing is that it's the CFM per square foot metric is a more accurate way of talking about leakage. You can think of it from the perspective of if I'm a painter and I'm painting all the walls of the building thermal envelope, I'm not going to measure the quantity of paint that I need by volume, really. I'm going to measure out the square footage of the wall area to understand how much paint I need to buy to paint those walls there. So kind of in the same way, when I'm using volume as the metric to talk about holes in the building envelope, I really need to be talking about the square footage of that building envelope and equating the holes to that square footage to get a better, more accurate understanding of how airtight that house is. So I agree that the metrics don't line up with each other, but it's still promoting our ultimate goal of trying to change the metric that people are using over time.
Gotcha. Okay. Let's see here. I thought you could put I I thought you could put the garage in the blower door test volume, but it's not preferred as the doors are leaky and not allowed for conditioned space in the HERS rating. I did not think there was anything you could not include the garage volume in the blower door test volume. I've seen garage doors installed in conditioned spaces of the house to the outside, but are not located in the garage.
Yeah. The garage is kind of the quintessential health and safety issue that's associated with the house and blower door testing. And because of that, very clearly in the IECC and the air barrier section and air barrier, air sealing and insulation installation section, it says very clearly that the garage needs to be separated from the house. And it's all because of health and safety. So if you're in a climate zone it's very common to use um, condition that space. That's where the confusion comes because the code talks about conditioned space, but it also talks about garages and whatnot. So basically, what it's saying is that the garage is always excluded from when you're doing the blower door test, but it's included when you're conditioning that space. You have to use, for example, the R value table in your climate zone when you're choosing the insulation that you're going to insulate that garage to there. So there's some confusion in the language, but the reality of what they're trying to get at is that you use the requirements of the code if you're insulating that space and conditioning it. You still have to do a manual J and kind of those types of things. But when you're doing the blower door test, it's always excluded because of the health and safety issue that's associated with the garage being connected to the house.
Thanks, Robbie. I know I asked you a similar question last week. Um, and just to mention, we are doing an IECC for garages training webinar as part of this series as well. So if you'd like to hear more about that, definitely recommend attending that. Okay, got two more questions. This one is in regards to passive house. I think we did a training on passive house, but it might be good to do a refresher course too.
Okay.
But this one is please discuss over and under pressure tests required by passive house.
Yeah. So when you're pushing air through a hole or um, pulling air through a hole, you can get slightly different results. And this is most often, I think you can think about it from a window perspective. So if you have a um, window that opens, for example, if I'm depressurizing that house, I might be closing that window if the latching mechanism uh, doesn't work as well as it should, for example. But if I pressurize the house, I might be I might be pushing air out through that window if it closes in that way. So that's ultimately what it's getting at there is that your leakage can be slightly different there. And from a passive house perspective, air leakage is such an important part of the equation because they're building their walls and assemblies at such high R values that they're lowering the condensation point, dew point of what we call the first exterior um, condensation point or dew point of the assembly that you have to better ensure that the air and air that's carrying moisture isn't moving into the assembly and then ultimately getting to where it's going to condense and create condensation inside that assembly. So their leakage target, the code is at 3 air changes in our climate zone. Passive house is down at 0.6 air changes per hour because they want to ensure that there's no air movement into those assemblies that where you might get the potential of condensation happening there.
Got it. Thank you, Robbie. Okay, last question for today. And folks, if you have more questions, don't hesitate to reach out to Robbie or utilize that Colorado Codes helpline. It's here as a resource, and Robbie is one of the subject matter experts that responds as well through that platform. Okay, this one is just in regards to the duct leakage to the outside testing requirements and thresholds in the 2021 IECC. Um, where are they? I only see duct leakage in R 403.3.5 and point 0.6.
And are you saying it's not in the IRC?
The IECC 2021 is what they're referring to. They're trying to understand where the requirements for that
For
outside
duct leakage
testing.
outside?
Yes.
Yeah, so that's that's the issue is that when you utilize the R405 and R406 sections in any code iteration, uh, the modeling allows you to take into account duct leakage to outside, but the code specifically didn't ever address it, except I think after maybe the 2009 ICC, duct leakage to outside was taken out of the code language, but it wasn't taken out of the modeling there. So in the 2024, it was brought back to ensure that jurisdictions knew that this additional test needs to happen if they're using those compliance pathways, and that just a random number wasn't utilized in the energy modeling there.
That's good insight, Robbie. Thank you.
Yeah.
Okay.
I,
Crammed a
s-
lot in.
yeah.
Sorry, do you have something else?
I saw one other question or comment about kitchen hoods. that is asking about, kitchen hoods. Most kitchen hoods are at 400 CFM or greater. And why isn't makeup air required, I think, to be tested? And I think that's a great point there, but it's not right now a requirement.
Got it. Okay. I'm gonna go ahead and end the recording.